Okay, so this video is looking at families of quadratic functions and also determining rules. And there's a bit of overlap in that because we're often looking at quadratic equations with various unknown coefficients and trying to find specific cases of those quadratic equations. So when we talk about a family of quadratic functions, or a family of any type of functions, we're looking at a group of functions, in this case quadratics, so x squared being the highest power of x, that all have common traits. Okay, they might have a lot in common, or they might not have much in common. So for example, in this first box that you're seeing here, you're seeing an illustration of some of the quadratics in the family of quadratics that are of the form y equals a times x squared, where a can be anything other than 0. Okay, obviously if a was 0, that would be the equation y equals 0, and it's not a quadratic function at all, so we need that qualifier. So these are all parabolas with their vertex at the origin. Okay, haven't been translated left or right, haven't been translated up or down, so parabolas with their vertex at the origin. And so we've just really got the dilation factor and possibly a reflection if a is a negative value. So we're just looking at all the different parabolas, tall and thin, really wide, really wide and fat, whatever it might be. You know, y equals pi x squared, y equals 3.8x squared, y equals 17x squared. All of the parabolas that fit this particular condition. So what you're seeing here is the family, the functions within this family where a is equal to 1, 2, 3, 4, 5, that's all the positive ones. This would be y equals 1x squared, so just x squared, y equals 2x squared, y equals 3x squared, y equals 4x squared, and y equals 5x squared. And we're also seeing the parabolas where a is -1, -2, -3, -4, -5, and that's going to be these upside down ones. Actually, I think we might be missing one of those. My apologies. I think, so this would be -x squared, -2x squared, -3x squared, -4x squared. I just think we're just missing that last one, that -5x squared, which would have been there. Okay, so we have this family of functions. They have these common traits, you know, same vertex. They have differing traits, you know, different dilation factors and possibly reflection in the x-axis. Here's another family of functions. They are all of the form y equals x squared minus bx. And again, where b can't be 0, because otherwise it's y equals x squared, which is more of this family than it is of this family. Okay, so these are all, if we ever think about y equals x squared minus bx, it has a common factor of x, so it's x times x minus b, which means it would have two x-intercepts, one at x equals 0 and one at x equals b. And because b can't equal 0, we'll ensure that it'll definitely always have two x-intercepts. One of them will be at the origin and the other one will be at whatever b is. Okay, so again, we're looking at, you know, any parabola, and again, the dilation factor is 1, so they can't be steeper and flatter. They're all going to be of the same shape, well, the same dilation factor, I should say, but we're going to potentially have, you know, an x-intercept at 0 and an x-intercept somewhere else. Okay, so it's not going to be, you know, a tall, thin parabola with those same two x-intercepts. It's going to follow the same kind of dilation as the others because they're all just 1x squared. But we're going to be seeing, you know, this family of quadratics. And again, here we've got that pictured for when b is 1, 2, and 3. So that's when we have x squared minus x squared minus 2x, and x squared minus 3x. And that's these three parabolas out here. And then when x is -1, b is -1, that would be x squared plus x, which will be this one, x squared plus 2, plus 2x, which would be this one, and x squared plus 3x, which would be this one. Alright, so that's what we mean by a family of quadratics. So let's have a look at an example here. A family of parabolas have rules of this form. Okay, so all parabolas, a can't be 0 because otherwise it wouldn't be a parabola. We've got plus 2 on the end, which means they'll all have a y-intercept of 2, because if we let x equal 0, we'll just get left with y equals 2. So they'll all have a y-intercept at 2, but that's about the only thing in common. They could be dilated differently, and because we've got a second variable as well, there could be a lot of things different about them. Okay, so part A is find the equation of the parabola in this family. So the equation has to take this form, that passes through the points 1, 0 and negative 1, 6. Okay, so whenever we have a point on a line or on a graph, on a quadratic, whatever it might be, all that is telling us is giving us information we can substitute into the equation. That tells us when x is equal to 1, y is equal to 0. So if we put that information in, okay, so 1, 0 means when x equals 1, y equals 0. And if we substitute that information into our equation, we get 0 equals a times 1 squared plus b times 1 plus 2. And so we get the equation 0 equals a plus b plus 2, or we might rearrange that to be a plus b equals negative 2. I'm going to call that equation 1 because we're going to get a second equation by subbing in our other point. So the point negative 1, 6 means when x is equal to negative 1, if that lies on the line, then for this equation, when x is equal to negative 1, y must be equal to 6. We sub that in, so y equals 6 when x equals negative 1. Okay, so 6 equals negative 1 squared is positive 1, so that's just a. Negative 1 times b is going to be negative b plus 2. I'm going to take away 2, so I'm going to have a minus b equals 4. And there's equation 2. And so I now have two simultaneous equations with two unknowns, which I can solve in order to find what a and b are. So I've labelled my equations 1 and 2. They're going to be easily solved by elimination, because if I add them together, the b's will cancel out. So I'm going to do equation 1, so I'm just going to move up over here. I'm going to do equation 1 plus equation 2. And when I do that, I'll get a plus a, which is 2a, b plus negative b, which is 0, which is why I chose to add, and negative 2 plus 4, which is 2. And so a will equal 1. And then I'm going to sub that into, I don't really mind, let's go into equation 1. So we're going to get 1 plus b equals negative 2, and so b is going to be negative 3. And so therefore, now let's be clear about what the question says. Did it ask us to find a and b? No, it asked us to find the equation, so we're going to make sure we've answered the question. So therefore y is equal to, ax squared, and a is 1, so that's just going to be x squared plus bx, and b is negative 3, so it's minus 3x, and plus 2. So that is the parabola that fits this family, okay, but that also goes through these 2 points. And you should be able to check that, you know, sub x equals 1 into here, you get 1 minus 3 plus 2, you get 0, okay. Sub x equals negative 1 into here, you get 1 plus 3 plus 2, and you get 6. Okay, part B. For a parabola in this family with its turning point on the x-axis, find a in terms of b. So again, remembering how we read the structure of a question. So the answers that we found in part A don't automatically apply to part B unless we're explicitly told that. To read part B, we read the stem of the question and then move straight on to part B. So the question says, a family of parabolas have rules of the form y equals ax squared plus bx plus 2 where a doesn't equal 0. For a parabola in this family, so by this family we mean this, with its turning point on the x-axis, find a in terms of b. Okay, so we want to think about what this means. So we've got our, if we know that we have the turning point on the x-axis, okay, so that means we're going to have a turning point somewhere here, you know, with coordinates, better not use a or b, let's say, you know, p0. Okay, so we want to think about, you know, what that might, how we can use that. Okay, so if we were to just substitute p0 into our equation, or whatever letter we want to use in place of p, so remembering that our equation is ax squared plus bx plus 2, that's not going to enable us to answer the question, because the question wants us to find a in terms of b. So that means if we sub this point in here, we won't have x or y anymore, but we'll have p and a and b in the equation. And so we won't have a in terms of b, we'll have a in terms of b and p. So that's not going to be the best way to think about it. So the other thing we want to think about is if the turning point is on the x-axis, so TP on x-axis means that there's only one x-intercept. So we know there's only one x-intercept, which means that we find x-intercepts by solving this equation. Okay, and so that means we need one solution to this equation in order for there to be one x-intercept, which would mean that the that the turning point is on the x-axis. So one solution to a quadratic equation is all about when our discriminant is equal to 0. So let's think about the discriminant here. And this is where methods is going to challenge you. You've got all these tools and you have to be able to use them, potentially in unexpected places. Okay. So this is what makes methods hard. It's not just about knowing what the discriminant is and how to calculate it. It's about thinking about how and where it can be useful in perhaps places where you weren't expecting it. Okay. So discriminant we know is b squared minus 4ac. So in this case that is b squared minus 4 times a and times c, which is 2. And we need that to equal 0 if this quadratic equation is to have one solution, hence this parabola is to have one x-axis intercept, which would mean that that intercept, if it's a parabola with only one intercept, the only way that happens is if it's the turning point. Okay. Alright, so we have b squared minus 8a has to equal 0. And the question asks us to find a in terms of b. Let's be clear about what that means. That means a equals, we want to find a. So it's not b equals, it's a equals. But it's not going to be a number, it's going to have b in it somewhere. Okay? So a has to be some kind of algebraic expression that involves b. As I said before, if it says find a in terms of b, it doesn't mean a in terms of b and other letters, it just means a in terms of b only. Okay, so we're in a position to do that. We want to make a the subject here, so I'm going to add 8a to the other side, but I'm going to write it the other way around, so we're going to have 8a equals b squared, and then to get a on its own, we're going to divide both sides by 8, so b squared divided by 8. So if the parabola has its turning point on the x-axis, i.e. if the parabola has one x-intercept, that will only happen if a is equal to b squared divided by 8. So for example, if b were to equal 1, a would equal 1/8, and that would mean that the parabola y equals 1/8 x squared plus 1x plus 2 would be a parabola that has its turning point on the x-axis. Let's just check that. Let's have a quick look at it. Control divide 1/8 times x squared plus x and plus 2. It indeed has its turning point on the x-axis. We could pick any other number. You know, if b equals 10, a is going to be 10 squared on 8, so 100 on 8. Which is 25 dividing by 4, 25 on 2, or 12.5. If we made that 25 on 2, and that 10x, let's edit it. 10x, 25 on 2. Again, a parabola with its turning point on the x-axis. Okay. If we made them negative, so if we looked at, if let's say b is negative 2, then a would be 4 on 8, which is a half, and so we'd be looking at half and negative 2. What we're actually seeing here is because we square b, even if b is a negative number, a is always going to end up being something positive. So these are always going to be positive parabolas, just by the condition that we've ended up with here. So again, if we look at minus 2x, and what was this equal to be? Half. Oh, sorry, must have changed something. Made it a cubic, not a quadratic. Ah, that's because I did multiply by negative 2x rather than subtracting 2x. Again, parabola with its turning point on the x-axis. Okay, so we've now got a connection between a and b, that as long as our coefficients of x squared and x, a and b, meet this connection, then we will have a parabola with its turning point on the x-axis. Okay, the second part of this video is determining quadratic rules, and a lot of the things we've just talked about in that those examples are relevant here. So we want to, if we've got a picture of a parabola or perhaps information about the parabola, be able to come up with the equation, okay? So the form of the equation that you start with is going to depend on the information you get. Even if you want to ultimately give your final answer in that form, if you've been given the turning point, you would absolutely start with turning point form, find the equation, and then expand it out to get it to look like that. Similarly, if you've got the x-intercepts, you would absolutely start with it in a factorized form. And if you know you need to give your answer in this form, then once you've got the equation, then you expand it out to get it in the required form. So don't let, if the question specifies what form you should give your answer in, don't let that determine how you start the question. Let the information that you have determine how you start the question. Okay, so if we have an equation, if we have the turning point, the best place to start would be an equation in turning point form. So turning point form is this: y equals a times x minus h all squared plus k. So we know that the graph is translated to the right by h and up by k, which is what means the turning point ends up at hk. Now in this case, k's ended up being a negative number, so it looks down there, but the turning point is going to be at hk. So if we have the turning point, we immediately know what h and k are, and then we just need another bit of information to find what a is. If we have the x-intercepts, now I'm going to change the letters we use here because I've used a and b and c here. A can be the same because all of these, if I expand them out, will have ax squared. I just don't want to confuse you with thinking that this b is going to be the same as this b. So let's just alter the graph. Let's make those points something really different. Let's make them p and q, for example. So we would have p and q in there. So if you know you have an x-intercept when x equals p, that means when you had the quadratic factorised, it must have had x minus p as a bracket. So that when you found the x-intercepts by letting y equal 0, and then you used your null factor law, x minus p equals 0, and so x equals p is one of your x-intercepts. Okay, so if you know the x-intercept is at p, you can work back to know what that means for the factor if the quadratic is factorised. Similarly, if x equals q is an x-intercept, x minus q will be a factor. Okay, so if we have the x-intercepts, we would start with a factorised form and then use some other information to work out the dilation. Because there are infinitely many parabolas that have these same x-intercepts, we would need another point to know which one is this specific parabola. Okay. And finally, if we don't have turning point, we don't have x-intercepts, we just have 3 points, we would start with the general form, and we would sub in our 3 points and generate 3 simultaneous equations in 3 unknowns and need to solve those. Generally speaking, we'll have our CAS if we're looking at this third situation, and we'll have a look at how to do that efficiently with our CAS when we get to the example like that further down the track. Okay, so let's work our way through these examples. Apologies. So determine the rule for the graph pictured. Okay, so here I've got the turning point. So I'm going to start with turning point form. Turning point form is y equals a times x minus h all squared plus k. If the turning point's at 1, 3, that means the equation is y equals a x minus 1 all squared to the right by 1 plus 3 because it's up by 3. Okay, so now we need to find a, and we've got another point here that we can use to find a. Okay, so we're going to substitute the point 0, 1. Okay, so we're going to sub 0, 1, which means when x equals 0, y is equal to 1. So 1 equals a times 0 minus 1 all squared plus 3. Okay, so negative 1 all squared is just positive 1, so that's just going to be a plus 3. Taking away 3, a is negative 2. Now, I'm happy that a is negative. I expected a to be negative because I have a sad parabola. Don't start by writing negative a though, or you'll confuse yourself later on. Just start with turning point form, sub in your points, solve for a, but know that you're expecting to get a negative a value if you have a sad parabola. Making sure we answer the question, so we want to determine the rule, so therefore answer our question. Y is going to be negative 2 times x minus 1 all squared plus 3. That would be the equation of this parabola pictured here. Okay, let's have a look at this one. Determine the rule for the graph pictured. This time we've got a parabola. We don't know the turning point, but we do know the x-intercepts. So I'm going to start with my quadratic in a factorised form. So I know if there's an x-intercept at 5, that's because x minus 5 must be a factor. Okay. If there's an x-intercept at -1, that's because x plus 1 must be a factor. And then I need to work out the dilation factor of the parabola that has x-intercepts here and here, but that hits this particular y-intercept, because there are infinitely many other parabolas I could draw with the same x-intercepts. I want to find the one that goes through 0, -5. So working out the dilation factor will tell me that. Okay, so we're going to substitute the point 0, -5. When x equals 0, y equals -5. -5 equals a times 0 minus 5 times 0 plus 1. -5 equals a times, that's -5 times 1. Okay, so actually in this instance a does equal 1, and so therefore the equation is x minus 5 times x plus 1. But if you just straight away wrote that down without putting the a up here, without thinking about working out or checking what the dilation factor is for this particular parabola, then you wouldn't earn full marks. Okay, you must consider it. Okay, it turned out to be 1, so it turns out that is our equation. But if you just happen to stumble across the correct answer by not knowing you needed to think about a, that's not worth full marks. Okay. Alright, and finally example 4, find the equation of the parabola that passes through the points 1, 4, -110 and 3, 14. Okay, it doesn't tell us that any of those points is the turning point, they're just points on the parabola. None of them are x-intercepts, because if they were x-intercepts they would have 0 y-coordinates. And so we just have 3 random points. Okay, so to be clear about what's happening here, what we would do is we would define a general quadratic. Okay, y equals ax squared plus bx plus c. And then we would sub in our 3 points. So if we sub in the point 1, 4, when x equals 1, y equals 4. So we get 4 equals a plus b plus c. When x equals -1, y equals 10. So we get 10 equals, now -1 squared is +1, so that'll be a. -1 times b is -b plus c. And 3, 14, when x equals 3, y equals 14. So 3 squared is 9, so it's 9a plus 3b plus c. And we've got 3 equations in 3 unknowns that we're going to solve simultaneously. Now, as I said, it's possible to do this by hand, it's just time consuming. You just have to deal with 2 equations at a time. So, you might, for example, subtract, you might do 2 minus 1 and that would eliminate c, and then you would do another combination of them, so you'd do 3 minus 2 and that would also eliminate c, and then you'd have 2 equations with a and b, and then you solve those, and then you sub those back in to find what c has to be. But realistically, as I said, it's not harder than solving 2 simultaneous equations in 2 unknowns, so it's not usually tested because it's just time consuming and we've got plenty of other things to test rather than testing this. So if you've got this, you would generally solve those simultaneous equations with your CAS. So let's have a look at how to do that, but then I'm going to have a look at, actually we don't need to do this much work ourselves, our CAS can do a lot more of it for us from the beginning. So menu 3.1, no sorry, my apologies. Menu 3.7.1, solve system of equations. We have 3 equations, and the unknowns in our equations are a, b, and c. And then we type our equations in here, so 4 equals a plus b plus c, tab 10 equals a minus b plus c, tab, and 14 equals 9a plus 3b plus c. Okay, and so we find by solving those simultaneously that a equals 2, b equals -3, and c equals 5. And so therefore putting that back into the equation to actually answer the question, which is to find the equation, means that our equation is y equals 2x squared minus 3x plus 5. That would be the parabola that goes through those 3 points. Okay, let's just be quickly clear about actually how we can do that more efficiently with our CAS, and it relies on us using function notation. Now we haven't introduced function notation formally in Year 11 yet, but it is something that you might be familiar with from Year 10. It's certainly something that I talk about in Year 10. There's an earlier Year 10 video called Function Notation and CAS that you might want to refer to. The advantage of using function notation is our CAS works very nicely with function notation, and it's therefore much quicker to do this process with our CAS. So if we instead define f of x as being ax squared plus bx plus c, if I want to substitute the point 1, 4 into f of x, i.e. let x equal 1, to let x equal 1, I do f of 1, which would replace all the x's with 1's, and then we would want that whole thing to equal 4. So f of 1 equals 4. We can just write that, and that literally represents that equation. That's what that says. F of 1 is a times 1 squared plus b times 1 plus c, so a plus b plus c, and it equals 4. Okay, so function notation is so valuable. It's not a CAS thing, it's a maths thing, and it allows for a huge amount of shorthand. It's really frustrating in the VCAR exams when they don't define the function in the question as f of x or g of x, and you then have to use much more time-consuming notation to be consistent with the question. It happened in last year's paper. I really disliked it about last year's paper. I'm talking about the 2020 paper. Okay, so the second point is negative 110. So if we want to substitute x equals negative 1 into the function, we're replacing x with negative 1, so that's f of negative 1, and that will mean we do a times negative 1 all squared plus b times negative 1 plus c, and once we've done that, that whole thing then has to equal 10. And finally, f of 3 is going to equal 14. They are our simultaneous equations, and our CAS can work from those. So if in our CAS we define the general function first, so that's a bit time consuming, defining this, but then the subbing in and the solving of the equations is quicker. Okay, so we're going to go menu 1, 1 to define a function. We're going to define f of x. You must use function notation. You can't just define f equals something. You won't then be able to use it in your CAS. So a times x squared plus b times x. Make sure you type those multiplication symbols, okay, plus c. If I didn't type those multiplication symbols, if I just left this one out, for example, or both of them really, but if I just typed ax squared plus bx plus c, my CAS will think ax is a single variable that's being squared, and then we're adding on bx, a single variable, and then we're adding on c. What you'll notice is if I type, so what you actually want is a times x, b times, a times x squared, b times x, and you must be explicit about that if your CAS is to understand what you mean, okay? You don't need to be explicit about multiplication, you don't need to be explicit about multiplication if you're talking about a number times x. If you type 2x, I haven't typed 2 times x, I've just typed 2x. When I press enter here, my CAS will reformat that as 2 times x, because it understands when I type a number followed by a letter, it means multiplication. That's the missing operation. However, if it is a letter next to a letter, it doesn't understand that I mean those letters to be multiplied together. It thinks I'm defining a variable called ax or a variable called books, you know. So you can use words as variables in your CAS, and so therefore, if you want 2 letters next to each other to mean that letter times that letter, you need to tell it that explicitly. So be careful about how you define your function to start with. I've defined f of x as a times x squared plus b times x plus c. So now I'm just going to show you this, but I also wouldn't do this. If I type f of 1 equals 4, it will sub 1 into the equation, make it equal to 4, and generate this equation here for me. If I type f of negative 1 equals 10, it will generate this equation that we did by hand. And I know these were easy to generate by hand, but imagine something more complex, okay? And similarly, if I did f of f of 3 equals, f of 3 equals 14, it would generate this third equation. And then I could solve the equations from there and copy and paste those equations into my simultaneous equations thing. So menu 371, 3 equations with 3 unknowns, a, b, c, okay, and then I could, now be careful about this because, okay, no problem here. If I scroll up from here and press enter, it'll copy the equation into there. If I now want to copy equation into this second box, when I scroll up from this second box, my cursor doesn't go to the line above, it goes to the equation above within the solve function. And then if I scroll up again, when I press enter on this equation, it's going to paste that where my cursor last was in the entry line. And that was up next to the A of the A plus, so it'll go up here, which is not what I want. So it's a little bit more fiddly, but you're going to instead do Control C to copy that line and Control V to paste it with precision where you want it. Control C, Control V, and you could do that. Now again, I wouldn't do any of that. I don't need to do this much work. Okay? I don't need any of these lines. I've just typed them in to show you that that's what those equations would look like. We never need to see what those equations look like. We can just define our variable, define our equation. Menu 371, we're going to solve 3 equations where the unknowns are A, B, and C. And then I'm literally just going to type f of 1 equals 4, because that is this. I don't need to actually generate the equation. I don't need to actually see the equation. My CAS can do it and solve it. F of -1, all in the one step, equals 10. And then this one, f of 3 equals 14. Great. And it will solve those 3 equations to find that A is 2, B is -3, and C is 5. And so therefore the equation is 2x squared minus 3x plus 5. So declare what f of x is equal to, the most general kind of quadratic, ax squared plus bx plus c. Generate your 3 equations, but you don't need to actually calculate them. You just, if I'm subbing 1, 4 into f of x, that means f of 1 equals 4, f of -1 equals 10, f of 3 equals 14. Get your CAS to solve those. It immediately gives you a, b, and c, and then you can write down the equation. You do not need to write solve using CAS. If you've got 3 simultaneous equations followed by an answer, we all know, and it's in an assessment where you have your CAS, we all know that you solved them, and we all know you must have used your CAS to do that. So you don't need to tell us when you're using the CAS, you just need to write good maths on the paper. Here's the general equation, here's where I subbed in my points to generate 3 equations, then I solved them to get the 3 answers. Okay? And then I've actually answered my question. So this little box here talks about how to do that. There's a different example in the screenshot there, but same idea. 3 points, general parabola, easily done in 2 calculations with your CAS. Okay, well, define the function and then 1 calculation. Okay, work today is from exercise 3K.